Welcome back to the deep dive. Today we are actually engaging in a bit of time travel.
Oh, yeah.
Yeah, we're going way back to 2018.
Which, I mean, let's be honest, in the world of AI, that feels like an absolute lifetime ago.
It really does.
Yeah.
Because you think about where we are right now. You just, type a prompt into a chat box and it spits out a sonnet about toaster ovens in the style of Shakespeare.
Right. Flawlessly.
Flawlessly. And we totally take that for granted. But our mission for this deep dive is to look at the specific moment, the actual research paper that made all of that possible.
Yeah, the foundational stuff.
Exactly.
So we are talking about a paper called Universal Language Model Fine-Tuning for Text Classification.
Right.
Or ULMFT for short, which is a lot easier to say.
Definitely.
And it was written by Jeremy Howard and Sebastian Reuter.
And the claim we're making here, the setup for today, is pretty big. We're saying this paper is essentially the ImageNet moment for text. Like, it is the bridge between the old way of doing things, which we'll unpack, and the massive generative AI revolution that you and I are swimming in today.
I think that's a completely fair claim. But to really understand why this paper was such a shockwave, you have to sort of understand the landscape of early 2018.
Okay, set the scene for us.
It was really a tale of two cities. If you were working in computer vision...
Teaching computers to see.
Right, exactly. If you were doing that, you're popping champagne.
Yeah.
But if you were working in NLP, natural language processing, teaching computers to read...
You're struggling.
You're basically still banging rocks together.
Okay, so let's talk about the champagne poppers first. What was computer vision doing right that the text people just weren't doing?
Well, they had cracked the code on this concept called inductive transfer learning.
Inductive transfer learning.
Right.
That sounds like one of those phrases I would just nod at in a meeting while secretly Googling it under the table.
Most people do.
So what is it actually?
It's surprisingly intuitive once you break it down. So imagine you want to train an AI to recognize a specific breed of dog.
Oh.
Let's say a Scottish Terrier.
Okay, cute dog.
Very cute. In the old days, you would need thousands and thousands of pictures of Scottish Terriers to teach the computer what one looked like, right from scratch.
Which is just a huge amount of data gathering.
Huge. But by 2018, computer vision researchers weren't doing that anymore. Instead, they were using models that had already been pre-trained on a massive dataset called ImageNet.
Ah, right, ImageNet.
Yeah, which has millions of images of literally everything.
Yeah.
Strawberries, suspension bridges, aircraft carriers, you name it.
So the model had effectively already gone to vision school.
Exactly.
It knew what an edge was or a curve, how shadows fall on an object.
It had learned the fundamental visual physics of the world. So when you wanted to teach it to spot your Scottish Terrier, you weren't teaching it how to see from zero.
You're just refining it.
Right, you're taking this incredibly educated brain and just saying, hey, apply all that broad knowledge to this one specific dog breed.
And that works well.
It's wildly efficient, it's fast, and it requires very little new data.
That makes total sense. I mean, you don't reteach a human how to see every time you hand them a new object.
Exactly.
But you're saying the NLP folks, the language people?
They did not have this.
Yeah.
No. In NLP, almost everyone was still training from scratch.
Like tabula rasa, blank slate.
Pretty much a blank slate. Say you wanted to build a spam filter for your email. You would initialize a model with random weights, literally a blank brain.
Okay.
Then you'd start feeding it your spam emails. And that poor model had to figure out two incredibly complex things at the exact same time.
Oh, boy.
First, it had to figure out the entirety of the English language. Grammar, syntax, what a verb is, what a noun is.
Right.
And second, it had to figure out what spam looked like.
That just seems wildly inefficient. I mean, that's like trying to pass the bar exam. But you're being forced to learn the English alphabet at the exact same time you're studying constitutional law.
That is the perfect analogy. And because you're asking the model to do both of those things simultaneously, you needed massive data sets.
Right, because then needs enough examples to learn English and the law.
Yes. If you didn't have millions of documents for your specific task, your model just failed. It wouldn't work.
But wait, I feel like I remember hearing about things like word vectors back then, or word2vec.
Yeah, word2vec.
Wasn't that transfer learning?
It was, technically, but it was incredibly shallow. We refer to that as transferring word embeddings.
Okay.
It's kind of like giving the model a dictionary. It knows that the word king is mathematically related to queen, and Paris is related to France.
Okay, so it has vocabulary.
It has vocabulary, but it doesn't understand sentence structure, context flow, sentiment. It's literally like handing someone a French dictionary and asking them to write a French novel.
They have the words, but they don't know the music.
Precisely. They don't know how to string them together.
So ULMFiT comes along and basically says, forget the dictionary. We are going to transfer the whole brain.
Yes. Howard and Reuter proposed transferring the entire neural network, every layer.
So why hadn't anyone done this before 2018? Was it just that nobody thought of it?
Oh, people thought of it. But it was a technical nightmare because of a phenomenon known as catastrophic forgetting.
Catastrophic forgetting.
Yeah.
Honestly, that sounds like what happens to me after a really long holiday weekend.
Well, in a neural network, it's significantly worse. Imagine you take a model that knows English perfectly,
Okay.
and then you try to fine-tune it on a very specific task, like analyzing dense medical records. You
Right.
start updating the model's parameters so it can learn all the medical jargon. The problem is, deep learning models are very aggressive learners.
They just want to minimize the error.
Exactly. So in its rush to minimize the error on the new medical task, the model basically overwrites the foundational connections that held its general knowledge of English.
Oh, wow. So it learns what a diagnosis is, but completely forgets how to use the word the.
Effectively, yes. It cannibalizes its own general intelligence to solve the immediate specific problem in front of it.
That's fascinating.
Or if your data set is too small, it just overfits.
Meaning it just memorizes the data.
Right. It memorizes the specific medical records you fed it instead of learning any underlying patterns.
Yeah.
So the ULMFE paper wasn't just some manifesto saying, hey, let's do transfer learning for text.
It was a how-to guide.
It was a highly detailed manual
Yeah.
on exactly how to do it without lobotomizing the AI in the process.
Okay, so let's get into the how. Because I know they propose a 3-stage process, and I really want to walk through this carefully because I think this is where the magic actually happens.
It is.
So what is stage 1?
Stage 1 is general domain language model pre-training. This is the direct counterpart to that ImageNet training we talked about for vision.
Okay.
They took a standard architecture, specifically an LSTM, which is a type of recurrent neural network,
Right.
and they trained it on Wikitext 103.
Which is just Wikipedia, essentially.
Yeah, it's a cleaned up, curated version of Wikipedia, about 28,000 articles, or roughly 103 million words.
And what is the model actually doing during the stage? Is it trying to classify the Wikipedia articles by topic or something?
No, and this is a crucial distinction. It is just trying to predict the next word.
Oh, just next word prediction.
That's it. You feed it the phrase, the quick brown.
And it has to guess Fox.
Exactly. And by doing this over millions and millions of words, it naturally learns the deep structure of language.
Because it has to.
Right. It learns that if a sentence starts with the phrase, the scientists, the verb that appears 5 words later has to be plural. It captures the long-term dependencies and the hierarchy of language.
Okay, so this is literally the P in GPT, generative pre-training.
It absolutely is.
Yeah.
So at the end of stage 1, the model doesn't know anything at all about your specific problem. It doesn't know about spam detection or sentiment analysis.
But it is completely fluent in English. Okay, so we have a fluent model. Now, naturally, you'd think we just jump straight to training it on our specific task. But ULMFiT introduces this middle step, stage 2.
Stage 2 is target past language model fine-tuning. And honestly, this is the step that most developers miss or skip today. But it is the absolute secret weapon if you have a small data set.
Explain this one to me. Because on the surface, it sounds redundant. You've already learned English from Wikipedia. Why do you need to learn language again?
Well, think about the difference between a Wikipedia article and, say, a movie review on IMDb.
Oh, I see. One is very formal, very encyclopedic, and the other is just full of typos, heavy slang, all caps, exclamation point.
Precisely. The distributions of the language are wildly different. If you take your pristine Wikipedia-trained brain and drop it straight into the chaos of IMDb, it's going to be confused.
It's going to experience culture shock.
Culturally and syntactically. So in stage 2, you feed the model the text from your target domain, the movie reviews, and you just ask it to keep doing the exact same thing it was doing before.
Just predicting the next word.
Just predicting the next word. You're not asking it to classify anything yet.
Wait, hold on. So you're just feeding it raw, unlabeled reviews. You aren't telling it which ones are positive and which ones are negative.
Correct. No labels at all. Just the raw text.
But if it's unlabeled, isn't it just reading gibberish? How does that actually help it solve the problem later?
It helps because it attunes the ear of the model to the specific dialect of your dataset.
Oh.
Let's go back to your legal analogy. Stage 1 was learning English. Stage 3 will eventually be judging the case. Stage 2 is just sitting in the back of the courtroom listening to lawyers talk for a week.
You aren't judging anything yet.
No, you're just getting used to the jargon, the sentence structure, the specific way they use words like heretofore and subsequently.
Ah, I see. So when it's finally time to judge, it isn't distracted by the slang. It expects the all caps and the typos.
Right. And the really beautiful thing about Stage 2 is that you can use unlabeled data for it, which is everywhere.
What do you mean?
Well, let's say you want to build a classifier, but you only have the budget to manually label 100 reviews as positive or negative.
Which is a tiny data set.
Very tiny. But maybe your company has 50,000 raw reviews sitting on a server somewhere that no one has ever looked at or labeled.
Right.
You can use all 50,000 of those raw reviews for Stage 2. It makes the model incredibly robust to the language of your domain before you ever even try to teach it the difference between good and bad.
That is so clever. You're squeezing value out of the data that usually just gets thrown away.
Exactly.
Okay, so now the model is fluent in general English, and it's practically a native speaker in movie review dialect.
Yes.
Now we finally hit Stage 3, target task classifier fine-tuning.
This is the final step. We take that pre-trained, heavily fine-tuned brain, and we slap a brand new final layer on top of it.
The classifier.
A classifier. And its only job is to take all that deep understanding and make a simple binary decision. Positive or negative.
But this is where the danger comes in, right?
Yeah.
This is where catastrophic forgetting usually strikes.
Yes, this is the danger zone.
Ugh.
You have this highly delicate, deeply trained brain. And now you're about to start training this completely new, clumsy classifier layer on top of it.
Right.
If you just hit run with standard machine learning settings, the mathematical shock of that new training process will ripple down and wipe out the knowledge in all the lower layers.
So this is where we get into the secret sauce. The paper outlines some very specific techniques to stop this brain wipe from happening.
They do.
The first one they call discriminative fine-tuning.
It's a fancy name for a very intuitive idea. In a deep neural network, we know that different layers capture entirely different types of information.
Right.
The bottom layers, the ones closest to the raw input, they capture very basic things. Simple syntax, basic word associations.
It's like the absolute foundation of the language.
Right. The higher layers, further up the network, capture semantic meaning, complexity, abstract concepts.
Okay.
So Howard and Reuter looked at this and argued, why on earth are we using the exact same learning rate for the entire brain?
What do you mean by learning rate, for the listener who might not know?
Think of the learning rate as how much you allow the model to change its internal beliefs based on new information.
Okay.
A high learning rate is a major tear-down-the-walls renovation. A low learning rate is just dusting the shelves.
Oh, I like that. Dusting the shelves.
Yeah.
So if the bottom layers already know the absolute basics of English perfectly well from reading all of Wikipedia,
You don't want to renovate them.
you just want to dust them.
Exactly. But the top layer, that brand new classifier we just added,
That needs a gut renovation.
yes, it doesn't know anything yet. So discriminative fine-tuning is basically giving different layers different permissions to change.
That makes perfect sense.
They actually used a specific formula where each layer has a learning rate that is exactly 2.6 times smaller than the layer above it.
Wait, 2.6?
Yeah.
That seems oddly specific.
It's entirely empirical. They tried a whole bunch of numbers, and 2.6 just worked the best.
That is machine learning for you sometimes, I guess.
It really is. But it works beautifully. The top layer learns incredibly fast, the middle layers learn much slower, and the foundational bottom layers barely change at all. It respects the foundation while letting you build the attic.
Brilliant. So that protects the layers spatially, basically. But then they introduce a technique for the actual timing of the training, slanted triangular learning rates, or STLR.
Right. This solves a major convergence problem. Usually when you train a model, you might just keep the learning rate steady the whole time or maybe slowly decrease it.
Right.
But Howard and Reuter wanted the model to settle into the right zone of the parameter space very quickly and then refine itself carefully.
Why is it called a slanted triangle?
Because of the shape of the graph, if you plot it out. Imagine the learning rate starts at 0. Then very quickly, for just the first 10% of the training, it shoots straight up.
A steep lineup, like a fast warm-up.
Yes, a very fast warm-up. This sudden spike in energy kicks the model out of its initial rigid state and pushes it rapidly toward the general area of the correct solution.
What happens if you don't do that?
If you don't do it, the model can easily get stuck in what's called a local minimum.
Which is what?
It's basically getting trapped in a small, shallow valley of error instead of finding the deepest ocean of truth. You have to give it a hard shove to get it over the initial hills.
Okay, so you shove it hard to get it moving, And then what's the slant part?
Then you spend the remaining 90% of the training time slowly, linearly decreasing the learning rate back down to 0. That long, slow decay is the slant.
So it's like, imagine exploring a brand new city. You run really fast to get to the correct neighborhood.
Right.
But once you're in the neighborhood, you walk very slowly and carefully to find the exact house number so you don't overshoot it.
That is a phenomenal way to visualize it.
Yeah.
Rapid convergence followed by very careful refinement.
Okay, so technique number 3 seems to be another massive safety rail against catastrophic forgetting. Gradual unfreezing.
Yes, and this works perfectly in tandem with the other techniques. Because even with the different learning rates, if you start training all the layers at the exact same time, the gradients, which are the signals telling the model how to change, they can be really noisy and destructive.
It's just chaos in the system.
Right, total chaos. So gradual unfreezing is exactly what it sounds like. At the very start of stage 3, you completely freeze the entire pre-trained brain. It is locked.
Locked down.
You only train the final classifier layer for one full epoch.
So the brain is basically asleep, and only the mouth is learning how to speak.
Exactly. Then once that's done, you unfreeze the next layer down. Just one layer. Train for an epoch, then the next.
You're just waking the model up layer by layer from top to bottom.
Layer by layer.
Why is this so much better than just letting the whole thing rip from the start?
Because it allows the new classifier layer to align itself with the pre-trained features before we start actively messing with those features. It entirely prevents the initial shock of the new task from destroying the pre-trained memories.
It really sounds like waking someone up from a deep sleep. You don't dump a bucket of ice water on them, you just gently shake their shoulder, let them open their eyes.
It's gentle, and it's incredibly effective. It was vastly superior to previous methods people tried, like chain thaw, which would unfreeze one layer but then refreeze the others. This method eventually has the whole model open, allowing for true holistic fine-tuning.
Amazing. Now, there is one last technical nugget in the secret sauce that I really want to hit because the logic behind it is just so cool. Concat pooling.
Oh, yes.
This addresses the problem of reading really long documents, right?
It does. In a standard recurrent neural network, like the LSTM they were using, the model reads the text sequentially, word by word by word.
Right.
And usually the classifier only looks at the hidden state of the very last word to make its final decision.
Which seems incredibly risky. I mean, think about it. If I write a scathing 500-word review about how a movie is absolute trash, but then I end the very last sentence with, "But I guess the popcorn was okay,"
Right.
the model might only really see popcorn was okay and flag it as a positive review.
Exactly. The information gets squashed or lost over long sequences. The signal from the beginning of the document just fades away.
So how did ULMFiT fix that?
They introduced concat pooling. They decided, we're not just going to take the last state. We are going to take 3 distinct states.
Walk us through the 3.
First, the last state, which is exactly how the document ended. Second, they took the max pooled state.
Max pooled, meaning?
Meaning it represents the absolute strongest signal found anywhere in the entire document.
Most extreme moment.
Right. And third, the mean pooled state, which is just the mathematical average signal of the entire document's history.
I love this concept so much. It really reminds me of asking someone how a party was the next day.
How so?
Well, the mean pool is just them saying, oh, the vibe was generally pretty good.
Okay.
The max pool is them saying Uncle Jerry broke a glass coffee table.
Right.
And the last state is, I was kind of tired when I left.
That is strangely specific, but yes.
You really need all 3 of those pieces of information to actually understand what happened at the party.
You do. And by concatenating or linking those 3 signals together, the classifier gets a much richer panoramic view of the text's actual sentiment. It doesn't miss the forest for the trees.
Okay, so let's summarize where we are. We have the 3 stages: pre-training, target language tuning, and classifier tuning.
Yeah.
And we have the secret sauce, discriminative tuning, slanted triangles, gradual unfreezing, and concat pooling.
That's the recipe.
The big question is, did it actually work, or was this just a bunch of theoretical gymnastics?
Oh, it worked. It worked remarkably well. The results were quite startling at the time.
Give us the numbers.
They tested it on 6 major data sets, things like IMDb reviews, Yelp reviews, AG News topic classification, and they reduced the error rates by 18 to 24% on the majority of them.
And were they competing against slouches? Like, what were they up against?
Not at all. They were beating the absolute state-of-the-art at the time. And remember, ULMFiT used a very standard, fairly simple architecture, an AWD LSTM.
Right.
They were consistently beating models that were highly engineered, incredibly complex, and used fancy new attention mechanisms.
So it definitively proved that how you teach the model is actually more important than the physical brain structure itself.
At that moment, yes,
But,
absolutely.
but there's one stat in this paper that I think is the most important one for our listeners, the killer stat, the sample efficiency.
Yes, the democratization stat.
Walk us through that.
So on the IMDb dataset, ULMFiT was able to match the performance of a model trained from scratch with 10,000 examples.
Okay.
But ULMFiT achieved that performance using only 100 labeled examples.
Wait, repeat that. It matched a 10,000 example model with only 100 examples.
Yes, 100 examples.
That is literally a 100x data efficiency gain.
It is. Think about what that actually means in the real world for a small business or a solo developer.
Right, because before this, if you wanted to build an AI to, say, classify customer support tickets, you had to manually read and label thousands and thousands of tickets.
And nobody has the time or the money for that.
No.
ULMFiT showed that you could take a pre-trained model, labeled just a tiny handful of tickets, maybe an hour's worth of actual human work, and get world-class, state-of-the-art performance.
And that's entirely because of that stage 2 magic we talked about.
Exactly. The model already knows English, and it already knows support ticket language from reading the raw text. It just needed 100 quick hints to figure out what you wanted it to do.
It completely opened the door for NLP to be used everywhere, not just locked inside giant tech companies with armies of data labels.
It leveled the playing field overnight.
I want to zoom out a bit as we get toward the end here. We've been talking a lot about LSTMs today, but if you look around today, everything is transformers. BERT, GPT, Gemini.
Right.
Did ULMFiT just get lucky for a minute, or did it actually set the stage for the transformer era?
It absolutely laid the foundation.
Okay.
The architecture of the LSTM, that did eventually get replaced by the transformer, mostly because transformers are much faster to train in parallel. But the process, the fundamental paradigm, that is pure ULMFiT.
The pre-train then fine-tune loop.
Yes. When BERT came out shortly after this paper, it was essentially just applying the ULMFiT strategy to a transformer architecture.
Wow.
And even today, when we talk about prompt engineering or RLHF, reinforcement learning from human feedback with models like ChatGPT,
Yeah.
we are still entirely operating in the shadow of this paper. We are taking a massive generalist brain and carefully fine-tuning it to behave in a highly specific way.
It's funny, we focus so much on the T in GPT, the transformer part, but
Yeah.
this paper really solidified the P, the pre-training.
And the F, the fine-tuning.
Very true. So synthesizing all of this, we started with NLP being the poor cousin of AI, really struggling to keep up.
Yeah.
And ULMFiT proved that inductive transfer learning was finally possible for language.
By deeply respecting the pre-trained knowledge, by using discriminative fine-tuning to treat layers differently, and slanted triangular learning rates to actively manage the energy of the training.
And gradual unfreezing to just gently wake the model up.
All of it combining to create a method that was drastically more efficient than anything that came before it.
It really was the major turning point. But before we wrap up today, I have to ask you, looking back at this 2018 paper from our vantage point today, what is the lingering thought for you?
We are currently in an era of bigger is better. Trillion parameter models. Massive compute clusters that literally consume the energy of small nations.
The Godzilla strategy of AI.
Exactly. Just throw compute at it.
Right.
But ULMFiT showed that a relatively simple architecture, a standard 3-layer LSTM, could beat highly complex, heavily engineered models just by being trained smarter.
Right.
By strictly controlling the learning rates and the schedules.
So do you think we are getting lazy today?
I do wonder if we are overlooking massive efficiency gains that could come from smarter training schedules in our modern giants. Are we just throwing hardware at problems that could actually be solved with better technique?
That is a deeply provocative thought. Maybe the next big revolution isn't building a bigger brain, but designing a better curriculum.
I strongly suspect it might be.
Well, on that note, we will leave you to ponder whether you need to study harder or just study smarter using a slanted triangular schedule.
Just don't forget to unfreeze gradually.
Words to live by. Thanks for joining us on this deep dive.
Pleasure as always.
See you next time.